All right, and we're back with a couple more examples from Advanced Algebra 11.1, which is on polynomials. Example 2 here, we have a polynomial function p, which says p of x is equal to x to the fourth plus x to the fourth plus 8 times x to the third plus 20 times x squared plus 16x. This is a polynomial. If I just look at the expression here, this is a polynomial. We have variables in x. They're all x variables, and then we have integer exponents, and this is already in our standard form, exponent of 4, 3, 2, 1, and then we don't have a constant term here. Still a polynomial, because it's a sum. We're adding together more than one term, which is one thing that the definition doesn't really lay out for us very clearly, but a polynomial has to be a sum of terms, so there has to be more than one term, and there is, and we can't combine these terms, so we have what is called a polynomial. And it's a polynomial function because it's defined as p and p of x, where we can plug in a value in for x and then evaluate that function at that value. And as you saw that just showed up a second ago, we're going to evaluate p of -1, which just means we're going to plug in -1 in for x and find out what is the value of this polynomial function at the value of -1 for x. So we're just going to do our basic algebra, and we just have a polynomial to deal with here. So p of -1 is going to be equal to -1 to the fourth plus 8 times -1 to the third plus 20 times -1 squared plus 16 times -1. So all I did here was take our polynomial function and replace all the x's with -1 because we're evaluating this polynomial function at -1. So that's all I did here. All the x's became -1s. Notice I put the -1 in parentheses around the where the x was, because that whole -1 is replacing x. So we have this, and now we're going to simplify just using order of operations exponents to do so. So we get this function here, or this expression, where we have -1 to the fourth power is +1. Because if we have a negative number to an even exponent, it's going to come out as a positive, and it's a -1 to the fourth, which is just going to be 1. The opposite happens here. We have an odd exponent to a negative, from a negative base, so it's going to be a negative number, and 1 to the third is 1. -1 squared is +1, and then 16 times -1, there's no exponent here, it's just going to be this -16 that I have right there. So, simplify further, you can do some multiplication. 8 times -1 is -8, 20 times 1 is 20, and then we have the 1 and the 16 still hanging out there because we didn't do anything with that. And now from here, just order of operations, right to left, or left to right, and we just add these together. 1 minus 8 is -7, plus 20 minus 16 is going to be -3. So what that means is that p of -1 is equal to -3 for this polynomial function. And then what we're asked to do here is we're asked to graph this function in the window -5 to 2 for the x values and -5 to 4 for the y values. So I did this on Desmos. Here's the picture of that, the screen grab of what I did in Desmos. And how I did this was I just plugged in this function into the function bar there on the side of where that in Desmos, and then I graphed it, and then I had to click this little wrench thing, and then you can adjust the window settings. That's exactly what I did. So you can see from the x values, we go from -5 all the way to +2, which is what we're asking for. And then the y values, we go from -5, which you can't see, but it's right there, all the way up to +4. And this is this function right here, x to the fourth plus 8x to the third plus 20x squared plus 16x. This is the curve. This is what we get. This is what this looks like. It's a quartic function, which we'll talk about later. And this is what quartic functions will look like. And then these coefficients change that, but this is a general idea of what that looks like. And we can verify this value here. P of -1 is equal to -3, which means if I have an x value of -1 right here, where the function lies is right there, and that is right at where -3 is. So the fact that this is lying on this graph is not a coincidence, because that's the function, and that's the value of the function, -1, -3. Next example, we have two functions here. We have two polynomial functions here. x squared plus 2x plus 1, and then we have 4x minus 5. And we're going to predict or evaluate the degree of f of x times g of x. So we're going to multiply these two functions together and then predict the degree or find the degree. If I'm looking for the degree of when I multiply these two polynomials together, what I'm going to do is I'm going to look at the largest degree here. The largest degree in this polynomial is x squared. The largest degree in this polynomial is x to the first. So when I multiply these two things together, the two largest degrees in each of the polynomials will result in the largest degree in the resulting polynomial. So if I have x squared and I'm going to multiply it by an x, I'm going to get x to the third. So the degree of f of x times g of x will be 3, and I get that 3 from doing x squared times x. And I pick those two because it's the two largest degrees, or the degrees of the two polynomials I'm working with here. Then I'm going to look at the leading coefficient of that same thing. Well, that leading coefficient is going to come from the same idea there. If I'm going to multiply x squared by x, these are the two largest degrees. I'm going to take the two coefficients of that, or the two leading coefficients, and I'm going to multiply those together. So the leading coefficient will be 12. And that 12 comes from 3 times 4. And why am I picking 3 times 4? Because 3 and 4 are the leading coefficients in these two polynomials. Then we can complicate things a little bit further. Now we're going to find or predict the degree of f of g of x. So that means we're going to put g of x, this 4x minus 5, into the x values in this function. So we're going to take this 4x minus 5, we're going to plug it in to x, and then x here, and then we're going to evaluate the degree of that. So I'm going to take this right here, and notice this degree is 1, and I'm going to plug it into the largest degree. That's where the largest degree is going to come from. So I'm looking at the largest degree to the largest degree. And now we're going to do basically the power of a power here. So we're taking x, we're plugging it into x squared. So we have x to the first being plugged into an x. So first to the second will result in the largest degree being 2. And that 2 comes from essentially x to the first to the second power. The largest degree to this largest degree, which is 2. 1 times 2 is 2. So when I plug that in to this value, that's what I would get. And then the leading coefficient of that would come from exactly plugging in this 4x minus 5 into here. So that's where that largest degree is going to come from. So I'm essentially going to have 4 will be squared, and then I'm going to multiply that by 3. So 4 squared times 3, 4 squared is 16, times 3 is going to be 48. So the leading coefficient of f of g of x is 48. And that might be less clear. Might be more helpful if we actually evaluate that to show exactly where that came from, which we can do.